Hello, all. Dr. Caudell back at you for part two. Chapter 5 is continued now. So, this next topic in chapter 5 is using the ideal equation of the state. So, as has been mentioned in part 1, we really don't want to work in Celsius. We want to convert it into Kelvin. So, in degrees Celsius plus 273 or plus 273.15 to be more accurate. Degrees C plus 273.15 to get into Kelvin. Get used to converting into Kelvin for these ideal gas law equations. So in part 1, we talked about Boyles Law. So in Boyles Law, the connection we could make is between pressure and the volume that gas occupies. So Boyle found that pressure and volume are inversely related. That means as one goes up, the other one must go down, and vice versa. So as pressure goes up, volume must go down. As pressure goes down, volume must go up. This was all the work of Boyle. So if a sample of gas is held at constant temperature, all this holds true. As long as we're not increasing the temperature or changing the number of moles of gas, so everything else is constant, then decreasing the volume of the container causes the pressure to increase. If a sample of gas is held at the same temperature again, increasing the container volume causes the pressure to decrease. It is important to credit what scientists we are learning about throughout the semester. So this is the work of Boyle. This is known as Boyle's Law. Something we'll see a little later in chapter 5 is this idea of partial pressures. So we have one gas that's present at P1. These white spheres, then these red spheres may represent a second gas at a certain pressure. We will find out later on, and we'll do this a lot more, do more practice problems, that the pressure total represents pressure 1 from the white spheres and pressure 2 from the red spheres. This means that pressures are additive. So if this gas had a pressure of P1, this gas had a pressure of P2, we combine them, the total pressure becomes this pressure value plus this pressure value. This is the idea of partial pressures. And so again, we'll come back and look a lot more at partial pressures and do some practice problems. So Boyle looked at pressure and volume. Next, in part 1, we also did cover Charles' law. So the connection for Charles' law is he found a connection between the temperature and the volume. He found that these are directly proportional, directly related. So as one goes up, the other must go up. And as one goes down, the other must go down as well. So Boyle's law was an inverse relationship, again, between the pressure and the volume. Now for Charles' law, it's a direct relationship between volume and temperature. So as we lower temperature, we're going to lower that volume. As we increase the temperature, this volume will increase relative to the initial starting point. So these top 3 images are looking at volume and temperature for Charles' law. So again, Boyle saw that pressure goes up, volume goes down, volume goes up, pressure goes down. We will start to connect the volume, pressure, and temperature now, as you can start to see in these 3 images down here at the bottom. So if volume is constant, as it is in these images, this part here is not expanding, it's not compressing the gas. So this stopper is remaining in the same position. Then we do have a connection between pressure and temperature now. So as volume is kept constant, again, that's what's happening in these 3 images. So as volume is constant, we lower the temperature, the pressure decreases. We raise the temperature, the pressure increases. So we won't just be thinking about pressure and volume and temperature in a vacuum, saying that non-coincidentally, because we're studying gases here, we're not just studying these in isolation. We will connect pressure, volume, and temperature all in one or multiple sets of equations. So we will eventually connect these variables. Next, we will learn about Avogadro's law. So as you would imagine, if Avogadro's name is in this law, then it must involve moles in some way. And so you're right, it does. Avogadro's law connects volume and the number of moles. So these are directly proportional based on Avogadro's law. So volume and number of moles are directly proportional. Other terms that were directly proportional we've looked at is Charles' law with volume and temperature. Now for Avogadro's law, as we remove some gas, that is the same thing as decreasing the number of moles of gas. The volume also decreases. As we add gas molecules, the volume increases. So in ideal gas law, we will start to see N. So N is the number of moles of gas. As we remove gas, we are decreasing N and volume is decreasing. As we're adding gas molecules, we're increasing the number of moles of gas. So that's adding gas molecules, increasing N, volume also increases, according to Avogadro's law, which we'll go into more detail later in chapter 5. And again, this is only if we're at constant temperature and constant pressure. So the only factors at play, if the only factors at play are the number of moles and the volume, then we see this relationship. If we start to decrease the temperature or change the pressure, that adds in a different set of variables. So we see this relationship when everything else is held constant. So with all these different gas laws, all these different scientists, I went ahead and included, I think, this nice table to help you see Boyles Law, Charles' Law combined, Gay-Lussac's, and then Avogadro's. So all these different scientists ended up making this proportionality either inversely proportional or directly proportional. They all helped shape these different formulas in studying gases. And again, just to point out, these hold true, these each respective equations hold true when these other variables are constant. If something else is changing, then we don't always have as straightforward of a relationship between moles and volume, for example. So one we won't talk too much more explicitly about, but we'll end up using this connection between pressure and temperature in solving ideal gas law problems is this equation here. So pressure and temperature are directly proportional. We'll use these different equations throughout and our ideal gas law that we'll get to. One example of this Gay-Lussac's law, so connecting temperature and pressure, this is a table, it's in your book, so it's showing that as temperature is increasing here, the vapor pressure of water also increases. If you go on to take General Chemistry 2, then you'll see that we'll study more on vapor pressure. So as temperature increases, vapor pressure also increases. This is just an example of Gay-Lussac's law that connects temperature and pressure as they are directly proportional. As one increases, the other increases. As one decreases, the other decreases. Now, I've been building up to all of these different various equations connecting Boyles' law, Charles' law, Avogadro's law. They would end up leading into this ideal gas law. This is a really important component of studying gases in chapter 5. So we can see the different components. Boyles' law, pressure and volume are inversely proportional. As one goes up, the other has to go down. That's why they're on the same side of the equation. Charles' law connects volume and temperature. As volume goes up, temperature goes up. As temperature goes down, volume goes down. That's why they are on opposite sides of this equation. Then lastly, Avogadro helped connect volume and the number of moles. So those are directly proportional. As volume increases, number of moles will increase. As the number of moles increases, volume increases. So these are directly proportional. And that holds true for both decreasing as well. So ideal gas law, all these different equations coming together, all these different relationships between the variables coming together, PV equals nRT, pressure, volume, number of moles, temperature. Then R is what is our gas constant. Depending on the units of these other variables, we will pick the appropriate gas constant, and again, we'll practice using this gas constant within the ideal gas law. So for the ideal gas law, there's this idea of standard temperature and pressure, or STP, you'll hear it as. At STP, If you hear the conditions are at STP, it means we're at 0 degrees Celsius and 1 atmosphere. We'll do some practice problems as well when we're told we're working at STP conditions and see how that dictates, okay, then we know what our temperature is right away and we know our pressure. Also, experiments show that at standard temperature and pressure at STP, 1 mole of an ideal gas occupies exactly 22.414 liters. So any ideal gas will occupy exactly this many liters. It doesn't matter what the identity of the gas is. If it's an ideal gas, it will occupy 1 mole of this ideal gas at STP will occupy about 22.4 liters. So that gas constant R, as we figure this out, what we plug in for this gas constant R is based on these values at STP. So we can apply this gas constant to other problems that aren't at STP, but how we figured out the value for the gas constant in the first place is using the conditions of STP. So at STP, we're at 1 atmosphere. At STP, we're at 0 degrees Celsius. 0 degrees Celsius plus 273.15 is how many Kelvin. Then we were told the volume of any ideal gas, 1 mole of any ideal gas, always occupies 22.4 liters. Then N is 1 mole. We took the ideal gas law and solved for R to get one variation of this gas constant R. So 0.08205 liters atmospheres over mole Kelvin. You will usually just see it as 0.0821, just as a slight rounding, but either value that you use should get you the right answer. This gas constant, this is in units, these specific units. We do have other gas constants with different variations of these units. So not always in pressure, not always in Kelvin. So you'll see different gas constants and I'll point them out as we go. So we figure out what gas constant to use based on the units that are given in our problem. If pressure is in atmospheres, then we'd use this gas constant. If somehow we have a pressure that's now in joules, then we might use this gas constant. So joule per mole Kelvin, 8.314 joule per mole Kelvin is another possible value for our gas constant R that you may need to use in solving these ideal gas law equations. Let's start practicing using that equation and see how things go. So a chemical engineer must calculate the maximum safe operating temperature. So we want to know a temperature of a high pressure gas reaction vessel. The vessel is a stainless steel cylinder that measures 47 centimeters wide and then 56.4 centimeters in height. The maximum safe pressure inside the vessel, so here's a pressure term, has been measured to be 8.30. What is this unit again for pressure? So that's Pascal, right? What is a capital M as far as prefixes go back to chapter 1? So MPa, this is megapascal, right? For a certain reaction, the vessel must contain or may contain up to 20.7 kilograms of chlorine, pentafluoride gas. So we don't have the number of moles. We don't have the number of moles, but we do have the mass of the gas. So 20.7 grams, kilograms, that's important. We will eventually need to convert that into moles to be able to plug that into our N in our ideal gas law. We also don't directly have a volume, but we can figure that out based on the volume formula for a cylinder. Ultimately, we're going to solve for temperature here. So we have pressure, we can get number of moles and volume, then we'll figure out what gas constant to use. Plug that into R, ultimately solve for temperature. So let's get everything into the right unit to be able to solve for temperature. So problems like this, you want to think ideal gas law. So in solving a problem like this, when you're given different variations of pressure, volume, number of moles, and we can also always plug in some value for R, our gas constant. So as I mentioned, these are the two main gas constants, our values for R that you should write down on your note card or be aware of. So joules per mole Kelvin, but then liters atmospheres per mole Kelvin. These are the most common values for R that you'll see and use in Chapter 5 problems. So we have our ideal gas law, PV equals nRT. We know we eventually want to solve for temperature, so we can always rearrange this ideal gas law to solve for our unknown. So we need to divide both sides by number of moles and the gas constant. Temperature is now equal to pressure times volume over N times R. So number of moles times a gas constant. When all the units work out, we will get temperature. For our pressure term, we were given that in megapascals, right? And we eventually want to use a gas constant that has units of either joules or atmospheres. Well, for us with megapascals, the best unit to go into is joules per meter cubed. Remember, pressure is just a force over some area, as was mentioned in part 1. So bringing us back to part 1, we do see pascals here into Newton per meter squared. We also see pascals into atmospheres. This is slide 6 from part 1, by the way. Because our gas constant R either has units of joules per mole Kelvin or liters atmospheres per mole Kelvin, then while we have Pascal, we should try to get this into a joule unit or atmospheres. So we definitely could have taken pascals, megapascals into atmospheres and used this gas constant value as well. But for more practice, let's also make this connection between pascals and joules, because currently that is not listed here in this box. So 1 Pascal is 1 joule per meter cubed. This is another pressure conversion that will be helpful to have. If you're wondering how we go between joule and Newton, well, if you're into physics, then you might remember that 1 Newton is 1 joule per meter. So this is how we can connect that 1 Pascal is 1 Newton per meter squared. But then because 1 Newton is 1 joule per meter, then really 1 Pascal is also 1 joule per meter cubed. Okay, so it's another pressure conversion you should write down. So 1 Pascal, 1 Newton per meter squared. 1 Pascal, also 1 joule per meter cubed. So we started out at 8.30 megapascals. Do you remember how we go between mega and then the base unit? For every 1 megapascal, that is 10 to the 6th Pascal, right? There's a whole lot of pascals in 1 megapascal. There's a whole lot of grams in 1 kilogram. There are 1,000 grams in 1 kilogram. So there are 10 to the 6th, a whole lot of pascals in a large unit like a megapascal. Now also from the last slide we were just on from part 1, we added this conversion that 1 Pascal is 1 joule per meter cubed. So 1 Pascal is really 1 joule per meter cubed. Megapascals get canceled out, so do pascals. That leaves 8.30 times 10 to the 6th joule per meter cubed. We needed to get rid of mega here, and then we converted pascals into a joule per meter cubed. Remember, pressure is just a force applied over some area. Now this is in joules per meter cubed, so not quite Newton per meter squared, but we saw how these units do connect. So this is our pressure term. Next, we can take that information about the cylinder we were given and get a volume term. So 47.0 centimeters in width, 56.4 centimeters in height. For the volume of a cylinder, it's pi r squared times the height. So the radius is not 47.0 centimeters, but 47.0 centimeters divided by 2, right? This is the distance of our diameter. So our radius would be 47.0 centimeters in half. Then the whole radius term is squared. Then the height of that cylinder is 56.4 centimeters. Seeing if all the units work out, we will square centimeters, then times another centimeter term. So that does check out that for our volume, we want it to be in a unit of length cubed, so centimeters cubed. Doing this math here and using the full value for pi, there should be a pi button in your calculator. Click that to get a more accurate answer rather than just typing in 3.14. So depending on what calculator you have, you probably do have a pi button you can type in. This comes out to 9.8 times 10 to the 4th centimeter cubed. Now, kind of going back to chapter 2, remembering how to deal with this cubed, and we want to get this into meter cubed. So the centimeter to meter conversion is for every 100 centimeters in 1 meter. Now, what do we do to get this into cubed, though? We need to cube this whole conversion factor that converts meters into centimeters. When we cube this conversion factor, we're going to have centimeters cubed from this, then times meters cubed over another centimeter cubed, just focusing on the units. That makes centimeters cubed and centimeters cubed cancel out, leaving meters cubed. So we need to cube 100. Take 9.8 times 10 to the 4th divided by first 100 cubed. When we take this number divided by 100 cubed, we get 0.097851 in meters cubed now. Now we have our volume term. We can plug in something for our gas constant. Once we look at the units again, we'll use either this gas constant or this gas constant. We're setting ourselves up to use this gas constant because we got that pressure in joules per meter cubed. Because joules is in our pressure term, we're going to use this gas constant. Now what's left is to solve for the number of moles, and we were given the kilograms of that gas. So 20.7 kilograms, let's first convert this into grams. So for every 1,000 grams, that's in 1 kilogram. So that's moving this over 1, 2, 3, so 20700 grams of the gas. Now, chlorine pentafluoride, how do we know what this is? How do we read this name and convert that into a formula? So chlorine, we list the first element. Penta, that means 5, right? Fluoride, we change the ending to IDE for this molecular compound. So naming and writing formulas from names is still going to come back throughout the semester. So chlorine pentafluoride, we should be able to see a name like this and write out the formula. So chlorine pentafluoride. From the periodic table, chlorine weighs 35.453 AMU or grams per mole, same thing. Looking at the periodic table for fluorine, that is about 19 AMU or grams per mole. So this number plus 5 times this number, we should get a molar mass of 130.453 grams per mole, or with a little bit of different rounding, we'd get this value here. I rounded off the mass for fluorine slightly, so we'll use this grams per mole to end up getting our number of moles to then plug into our ideal gas law. If we have this many grams of the gas, but we have this molar mass now, we can say 130.445 grams per mole. We want grams to cancel out. So we'll orient the molar mass like this. And again, I like to write it out so that I can see all my units get canceled out. So this gram amount multiplied by moles over grams, rather than showing it as divided by grams per mole. I think it's easier to visualize it like this. This divided by this is 158.69 with some other values here, some other digits, moles. Now we have our N term. N has to be in moles. So we can plug in N now. We do know that gas constant. Let's keep going and solve for temperature. Now here especially, it's really important to visualize all of our units and cancel out all of our units. I'm going to show you how I set this up. As you can see in Alex, it's stated as joules divided by meter cubed. I'm going to show you how I would write these units out, again, to better visualize what gets canceled out. Make sure we're doing the problem in the correct way. So 8.30 times 10 to the 6, I'm going to write it like this, joule per meter cubed. That is my pressure term. For the volume, we calculated that as 0.097851 meter cubed, right? That was using the volume of a cylinder to get this volume amount. As you can already see so far, meter cubed and meter cubed will cancel out. It's harder to visualize it when we write it like this. So that's why I recommend writing it out as I did here. This is all divided by the gas constant we want to use. Again, because we're in joules, then we should use the gas constant that has joules in it. If we were working in atmospheres, we'd want to use that other value for the gas constant. So whichever gas constant we use will depend on what units we see in our problem. We won't always use the same value for the gas constant for each problem. So that is 8.314 with some extra digits here, but I'm just going to write out 8.314. This is in units of joules. Then technically this is joules per mole Kelvin. So again, I like to write it like this so that I can better visualize what's going on with my units. If this is joules per mole Kelvin, then really the mole and Kelvin are on the other side of the division line. So I can write them up here, mole Kelvin. Oops, this should be a number of moles right here in the denominator. Temperature is PV times the number of moles times R. Now we need to account for the number of moles. So for the number of moles of gas, we calculated that we had to take the kilograms of gas, use the gas's molar mass by knowing the formula. Then we can plug in this many moles, so 158.69 moles of gas. Temperature better be in Kelvin or some temperature term at the end, so everything else needs to cancel out. Let's go through and check. Meter cubed, joules in the numerator, joules in the denominator here. Now, even another way I could have written this, I should have, is put meter cubed down here technically, because this is in our denominator. Either way, meter cubed always cancels out. I'm going to delete this one to not be confusing, but again, I could have put meter cubed down here in the numerator here. So now joules and joules cancels out as well, one in the numerator, one in the denominator. Moles and moles, leaving just Kelvin in our numerator. So this is how I'd cancel these out. I'm going to go ahead and write it down here as well to even better visualize meter cubed canceling out and to show you what I mean explicitly. So 8.30 times 10 to the 6 joule per meter cubed, that's in our denominator term down here with R and N. So meter cubed would cancel out. Again, I do like to visualize my units like this, as long as I'm being really careful about what I put in the numerator and what I put in the denominator. When we do all of this, we should get 615.54 with some additional digits in Kelvin. Be extremely careful about doing all the multiplication and division. Again, just write this out really clearly for yourself to make sure all the right units cancel out. Now we're left in Kelvin. Going back to our problem, let's see, calculate the maximum safe temperature in degrees Celsius, okay, and round it to 3 sig figs. So we had our temperature in Kelvin. Let's go ahead and convert that back into Celsius. So 615.54, keep all those digits if you can. Now we're going to subtract 273.15 to get our temperature now in Celsius. We should get 342.39 to just have 3 sig figs. Then this keeps 2 rounded down. This 39 does not round this up to 343. So our final answer is 342 in degrees Celsius. We had to go back and read that problem. So that was one variation of the ideal gas law. We had to convert temperature out of megapascals. We had to solve for volume of that cylinder. We had to solve for the number of moles of gas from kilograms. There is another example in your main slide deck. There's so many different variations of that ideal gas law. Maybe you need to solve for pressure, maybe solve for volume. So given different pieces of information, we can use that ideal gas law to solve for various variables. To do some more practice together, I want to go through a few more problems. So this is 5.4, example 5.4 in your book. Calculate the volume in liters occupied by 740 grams of ammonia. Do you remember what this is? Ammonia at STP. Ammonia, not to be confused with the polyatomic cation of ammonium. At STP, this is what I was talking about earlier. The conditions we know when we're told this is at STP is we're at 1 atmosphere of pressure and 0 degrees Celsius, or think of this right away because we would add 273.15. STP is at 1 atmosphere and 273.15 Kelvin. So if we're thinking this may be an ideal gas law, I also like to write out the ideal gas law and start checking off what variables we have. If we're told we're at STP, this tells us right away our pressure and our temperature. In the problem, the unknown is the volume. Then we don't have N, we do have the mass of ammonia gas. We can convert mass into moles. Then we can always figure out which gas constant to use to solve for volume. So we have everything we need here to solve for volume. So let's convert 7.40 grams of ammonia into moles of ammonia. Given the molar mass of nitrogen and 3 hydrogens, this is 17.03 grams per mole is the molar mass of ammonia. We would need to orient this such that 17.03 grams per mole, that's equal to 0.4345, some additional digits, moles of ammonia. We want to solve for volume, so volume is going to be equal to dividing both sides by pressure, nRT over pressure. We have 0.4345 moles of gas. The temperature is 273.15 Kelvin. The pressure is 1 atmosphere. Then which gas constant should we use? Moles, Kelvin, and atmospheres are here as our units. So moles, Kelvin, and atmosphere are in our units. Let's use this gas constant now because then we'll solve for volume in liters. So 0.08206 liters atmospheres per mole Kelvin. You might see it as 0.0821. The better way to use this gas constant is 0.08206 at least. This is the full value, but 0.08206 liters atmospheres per mole Kelvin. So let's use that version in solving our problem. So 0.08206, definitely running out of room here. Liters atmospheres per mole Kelvin. Now moles and moles cancel out. Atmospheres and atmospheres cancel out. Kelvin and Kelvin cancel out, leaving just our volume in liters. We should get 9.739 with some additional digits in units of liters. For just 3 sig figs, because that's the minimum number of sig figs in our original value, then volume will be equal to 9.74 liters. So using the ideal gas law, using what we know about STP conditions, that gave us a unit for pressure, a value for pressure, and a value for temperature. Then we converted grams into moles. Then we selected the appropriate gas constant to use. All of our units canceled out as we solve for volume by rearranging the ideal gas law. We're left with just liters. Then we did the multiplication and dividing by 1 to get this volume in liters. Now, I want to show you a slightly different approach, still based on the same principles of understanding the meaning of at STP. So if you're recognizing that 1 mole of an ideal gas occupies 22.41 liters at STP, then we could have taken the moles of gas, use this conversion factor. This is only at STP, by the way. It's only the special case. At STP, 1 mole of gas occupies 22.41 liters. We can use this conversion factor then, once we have the moles of ammonia, to then convert that into liters. You don't have to do it this way. If this way feels more comfortable to you, using the ideal gas law, plugging in the meaning for temperature and pressure, because we're at STP, it gives us the same answer. But let me show you continuing using this conversion factor specifically. So if we want to find the volume without having to bother with the gas constant, this is what we could do. So we have our grams of ammonia. We use the molar mass to convert this into moles of ammonia. Then if you'd like, you add STP, this conversion factor holds true. For every 1 mole of ideal gas, that's 22.41 liters. So then moles of ammonia cancel out, leaving just liters, again, because at STP, 1 mole of any gas, it doesn't matter the identity, occupies 22.41 liters. We still get the same answer as we did by using the ideal gas law, so just 2 different options in how you can approach problems if we're told we're at STP conditions. Next, I want to do this practice problem. So this is 5.6 in your book. We have argon, an inert gas. We are told the light bulb contains argon at this 1.2 atmospheres of pressure and 18 degrees Celsius. Then I'm seeing a second temperature at constant volume. Calculate its final pressure. So P1 is at 1.20 atmospheres. The initial temperature is at 18 degrees Celsius. Then we're going to be solving for a final pressure, or P2, given that the temperature increased to 85 degrees Celsius. And we are told we're at constant volume. We haven't yet done a problem connecting pressure and temperature, so I wanted to do this example with you as well. Going back up to this handy summary of this, the gas laws in this table, we want to use this equation, right, connecting pressure and temperature at constant volume and not changing the number of moles of gas. So P1 over T1 is equal to P2 over T2. So sort of a variation of Charles' law, more of a variation on Gay-Lussac's law, but we want to do P1 over T1 is equal to P2 over T2. So to give credit where credit's due, I'll fix this. I'll add in this scientist's name to this slide for you. And importantly, we're at constant volume and constant moles of gas, so then this relationship does hold true. Because we always want to work in Kelvin, to convert 18 degrees Celsius into Kelvin, add 273 or 273.15. That becomes our temperature 1. So P1 over T1 is equal to P2 over T2. To isolate P2, we want to multiply both sides by T2. So now I'm noticing this typo. So P2 is equal to P1 times T2 divided by T1. I apologize for these typos. I try to catch them from the book, but I did not catch this one. So I will fix this. I apologize. So P2 is equal to T2 times P1 over T1. Just to write this out really clearly. So now P1 is 1.20 atmospheres. T2 is also converting Celsius into Kelvin by adding 273. So 85 plus 273 is 358. I am very sorry about this additional typo as well. It is listed here, but this is incorrect. Then T1 is 291 Kelvin, so 1.20 times 358 divided by 291 is 1.48 atmospheres. So Charles' law, Gay-Lussac's law, then this combined version here, so connecting pressure, volume, and temperature. Again, it's going to be important to get really comfortable recognizing which equation to use. Do we use one of these, or do we use that ideal gas law? Then just be really careful with your units as well. I want to do one more practice problem here with you as well, so 5.7, just to get you comfortable using those different equations for gases. So the temperature and the pressure, we have T1 is 8 degrees Celsius at the bottom of the lake. P1 is 6.4 atmospheres. Then we're told a bubble starts to rise to the surface where the temperature at the surface is now 25 degrees Celsius. The pressure at sea level, as expected, is 1.0 atmospheres. Calculate the final volume in mils. We want the final volume of the bubble if its initial volume is 2.1 milliliters. We have not yet used one that connects temperature, pressure, and volume, so let's go back up to our table and see what equation we might want to use. So temperature, pressure, and volume is this combined law from Gay-Lussac and Charles. So P1V1 over T1 is equal to P2V2 over T2. This is when the number of moles of gas is constant, which we can assume it is because we're not told that one bubble combines with another bubble. We're just looking at the same bubble throughout the problem, so the same number of moles of gas in that bubble. So based on the information we're given at constant moles of gas, we're probably going to use this equation connecting pressure, volume, and temperature initially, pressure, volume, and temperature finally, or in their final conditions. It can be helpful to draw out a visual like this as well. It's up to you. I like to write out final initial conditions like this, but also it can be helpful to draw a fun picture where this is kind of the bottom of the lake and then it rises to the surface of the lake. Now, what temperature unit should we be prepared to calculate? We have it in Celsius. Well, we definitely are going to want to convert these into Kelvin. So we know we're going to convert these into Kelvin. We're also going to use that equation that we looked at, this equation that we looked at, because this is yet another version, but we get this by taking PV equals nRT for all the initial conditions. Gas constant won't change, so P2V2 over or equals N2R T2. If we solve for R for both cases, R is equal to P1V1 over N1T1. R is also then equal to P2V2 over N2T2, right? Dividing both sides by N1T1 and N2T2. Then because our gas constant is the same for all problems, we can use different variations of the gas constant. But if we assume we're using the same value, we can equate these, leading to P1V1 over N1T1 is equal to P2V2 over N2V2. So this is yet another variation of our ideal gas law. If you are given information about the number of moles changing as well, then you would need to use this equation. Because we're told number of moles remains the same, we do know we can use this combined law from Gay-Lussac and Charles. In fact, one tip could be to start with this one each time, and then if you say that the number of moles are constant, then that doesn't change on either side of the equation. If volume is constant as well, then we see we can get this relationship between pressure, pressure, and temperature. So really using this equation 5.9 could be helpful as long as you're comfortable canceling out what you need to cancel out and using what variables remain for your problem. So another really useful equation. We know for us the number of moles remains the same because that gas bubble is not combining with another gas bubble. It's still the same number of moles throughout the gas bubble rising to the surface. So for us, the number of moles remains the same. We cancel that out. We get to use this version of the equation. So as mentioned, we want to assign our final and initial conditions. We do always want to convert into Kelvin. So 8 plus 273 is this many Kelvin. 25 plus 273 is 298 Kelvin. So P1V1 over T1 is equal to P2V2 over T2. To isolate our only unknown, or volume 2, we multiply both sides by T2. So P1V1 times T2 over T1 is equal to P2V2. Then we divide both sides by P2. P2 cancel out, leaving volume 2 is equal to volume 1 times pressure 1 times temperature 2 divided by pressure 2 and temperature 1. So it gets a little more complicated algebraically, but here we have isolated for volume 2. Now we plug in all of our values. As long as we want to report the final volume in milliliters, we can just keep volume 1 in milliliters. That was 2.1 mils. P1 is 6.4 atmospheres. P2 is 1.0 atmospheres. So be sure also being really careful and plugging in the right values here. T2 is 298 Kelvin, T1, 281 Kelvin. Doing all this multiplication, canceling out atmospheres and Kelvin, leaving just mils, our final answer is 14 mils. Some checks we can do to make sure we're on the right track. Recall that volume is inversely proportional to pressure, and volume is directly proportional to temperature. Because the pressure decreases and the temperature increases, pressure decreases because we're going from the bottom of a lake to higher up in elevation. Whenever we are increasing in elevation, we're decreasing in pressure. Temperature is also increasing, we're told, as the bubble is rising. So ultimately, we expect the bubble's volume to increase. So the pressure is decreasing here. The temperature is increasing here. If pressure is decreasing, we expect volume to increase, right? Based on that relationship between pressure and volume from Boyles Law. Then as temperature is increasing, we expect the volume to also increase from Charles' Law, where volume and temperature are directly proportional. So with both Boyles' Law and Charles' Law, we ultimately do expect the volume to increase, and it does based on the value we got. It goes from 2.1 mils up to 14 milliliters for the volume of that gas bubble as it's risen to the surface from the bottom of a lake. So kind of a cool application of the ideal gas law to be able to calculate a volume of a bubble. I'm going to include an animation here at the end of part 2 on gas laws. I hope you're all doing well. Let me know if you have any questions. As always, I will talk to you soon for part 3. I'm also including here some animations that are copyrighted and they are provided by the publisher.
Consider a gas-filled container that has a movable piston. It is exposed to an atmospheric pressure of 1 atmosphere. Click on one of the buttons to see animations of how temperature, pressure, or the number of gas particles affects the volume that the gas occupies. You can increase the pressure by adding a weight on top of the piston. Let's add a weight that will increase the pressure on the top of the piston to 2 atmospheres. As the pressure on the gas increases, the volume that the gas occupies decreases. The volume that the gas occupies will continue to decrease until the pressure of the gas equals the external pressure on the piston, which is 2 atmospheres. The volume occupied by the gas will be half its original volume. You should see that the volume is inversely proportional to the pressure. V is proportional to 1 over P. Adding a proportionality constant K, we can write volume equals K divided by pressure, or pressure times volume equals K. This relation is known as Boyles' Law, which states that the volume of a fixed amount of gas is inversely proportional to the gas pressure at constant temperature. As the pressure on the gas decreases, the volume that the gas occupies increases. The volume that the gas occupies will continue to increase until the pressure of the gas is equal to the atmospheric pressure on the piston, which is 1 atmosphere. Let's use a Bunsen burner to increase the temperature of the gas. As the temperature of the gas increases, the volume that the gas occupies increases. In other words, volume is directly proportional to the temperature of the gas. We can write volume equals K times temperature, where K is a proportionality constant. This relation is known as Charles' Law, which states that the volume of a fixed amount of gas is directly proportional to the gas temperature at constant pressure. Note that as the temperature is doubled at constant pressure, the volume that the gas occupies When the Bunsen burner is removed, the temperature of the gas decreases, and the volume that the gas occupies decreases. The volume that the gas occupies will continue to decrease until the temperature of the gas equals the external temperature. Let's use a Bunsen burner to increase the temperature of the gas. As the temperature is raised, the average velocity of the gas particles increases. Thereby the frequency and intensity of collisions of gas particles with the container walls increase. Pressure, which is defined as the force exerted per unit of surface area, will clearly increase as the frequency and intensity of collisions increase. Pressure for a fixed amount of gas at constant volume is directly proportional to the temperature. Note that as temperature is doubled at constant volume, the pressure exerted by the gas when the Bunsen burner is removed, the temperature of the gas decreases. The average velocity of the gas particles decreases, thereby the frequency and intensity of collisions of gas particles with the container walls decrease. Pressure for a fixed amount of gas at constant volume is directly proportional to the temperature. Gas particles are entering the container. As the number of particles, or equivalently the moles of gas, increases, the volume that the gas occupies increases. In other words, volume is directly proportional to the number of moles of gas. We can write volume equals K times N, where N is the number of moles of gas and K is a proportionality constant. This relation is known as Avogadro's law, which states that at constant pressure and temperature, the volume of a gas is directly proportional to the number of moles of the gas. In this animation, the moles of gas particles is doubled, and correspondingly the volume occupied by the gas is doubled.